Let me kind of show you one thing that somebody did. That's my name, by the way. That's me. And he did this, not me. Okay, before we're going to start this thing, I'm going to pass, there's a pen here, this thing, and if you want to join our email list, so you hear about these kinds of events, please do. And if you don't, please don't. First of all, thanks for coming. And I must say that I'm totally overwhelmed. I mean, I didn't know there's so many nerds in Lawrence. Nerds of the world reunite, right? We're going to talk about something about general relativity, you know, about something that is esoteric and ununderstandable to even those who do it in some way. So I'm impressed, and thank you for coming. If you like the talk, you can thank Kristen. She's the one who organized all this. If you don't, talk to me. Okay, I'm going to just tell you what we're going to talk about today. So what is LIGO? Going to kind of talk about curved space-time, gravitational waves, non-primordial gravitational waves, detecting them, observing the universe in general, primordial sources of gravitational waves, what's so great about them, and what's happening in the future. As you can see, it's talk for nerds. I will try to explain all these words, but you probably heard some of them before. So first of all, what is LIGO? LIGO is an acronym for Laser Interferometer Gravitational Wave Observatories. And they were co-founded in 1992 by these three people that I suspect, no guarantees, but I suspect you'll see later on this year, we'll get the Nobel Prize in Physics this year for this discovery, unless we'll find out that this is a hoax and it's not real. Okay, the truth of the matter, before I start, I just want to add something that, as a physicist, I should. Okay? It's not a hoax, that's for sure, but on the other hand, other experiments may show that it's not exactly what it is. Okay, and that's always true in physics. And whoever comes and tells you this is a fact for sure, no questions, you know you're not talking to a physicist. Okay, everything in physics is up for questions. Okay, you do not have anything in physics that we know for sure. That's the way it's organized. It worked out pretty well so far. Okay, so actually, these people started talking about LIGO probably 20 years before that, but they actually managed to convince enough people, and especially the funding agencies, to build these things. And I'll show you what they are. But it became operational about 10 years after the first white paper about this thing, and demonstrated the proof of concept, mainly that it works. And it's as accurate as they say it is until 2010, for about 10 years. Then they shut it off for 5 years to upgrade it. And then they came up with what they call now Advanced LIGO. LIGO is designed to detect changes in distances, and I'll show you the exact apparatus and how it works, but to an accuracy of about 1/10,000th of the size of a proton. This is equivalent to measuring distance to the nearest star within a width of a human hair. The closest star to us is about 3¼ light years away, and if you can measure that to, well, maybe I'm old and my hair is a little bit thin, but your hair, okay? curved space-time. 1915, Einstein published his field equations. 1916, he actually published general relativity, but the field equations that determine general relativity were published in November of 1915. And this is basically general relativity. Okay? Matter tells space how to curve, space tells matter how to move. So when you have some kind of a mass, you warp space-time. And when space-time is warped and everything likes to move in straight lines, you'll start moving in straight lines this way. Because locally, that's what the straight line is. So if you ask each one of these balls, are you going around something? They will say, you're a fool. I'm going straight. Because for them, space is, that's the direction of straight things. Same kind of thing happens not only to mass, but to light. Light also follows what we call a geodesic, that always travels in a straight line, locally. Okay, so a straight line from here to here is this way. Okay, even though straight line from there to here is this way, but that's not local. Locally, everything travels in straight lines. So masses go around bigger masses, and light curves. That's what general relativity tells us going on. I'll tell you about what's happening locally. We have the apple, of course. Can't talk about gravity without the apple. Now you have forces up that is, oops, sorry. Let's start it again. Too many buttons here. Apples, there is gravity pulling it down, and there's a tree holding it up. So it's not moving. It's a straight line. That's according to Newton. Then what happens is it breaks from the tree and it falls in a curved line in time and space. General relativity says no, it's not. It's nonsense. There is no force of gravity. Okay, so there's no force of gravity. The apple that is hanging on the tree is feeling upward force, so it's curving up. It's not straight anymore. And then when it gets off the tree, it travels in a straight line. That's general relativity. So if you want to compare these two, straight line and a curve and a straight line. And if we want to make it compact, kind of thing, that's the way it looks, and you have the apple here and it's going to fall, and that's the difference in explanation between Newton and Einstein, between classical gravity and general relativity. So what's happening here is that you have a big mass, say the sun, and you have this one, the Earth, is going around because of the curvature of space-time, and Earth also has a little one, a little curvature, and the moon is going around that. Okay, and the galaxy, which is very, very far away, has a very, very big kind of what we call gravitational well, and the sun and the Earth and the moon and everything else is going around that. That's the way general relativity explains to you how things move. Okay, so what are gravitational waves? First of all, let's talk about what is a wave. A wave is a disturbance that travels through a medium. Gravitational waves are disturbances that, or distortions of space-time that move through space-time. Exactly the same. Here you have an ocean. That's a medium, and you have the ocean waves. They move through it. Here you have gravitational waves, disturbances of space-time moving through space-time. Fun fact, Gravity waves are waves that are caused by gravitational effects, like ocean waves. Gravity waves are not gravitational waves. Okay? We're trying to confuse you, I know, but that's the way it is. So when somebody talks to you about gravity waves, they mean ocean waves, something that is caused by gravity. Gravitational waves are caused by something else. We'll talk about that in a few minutes. Okay, when you have accelerating masses, they change the distortion, because if you have a mass, there is a distortion around it. If you accelerate it, the distortion is moving around with the mass. Okay, so when you have accelerating masses, you create gravitational waves. You have these masses here in the center. Two of them, they move around each other, they accelerate, and they create gravitational waves. It's very similar to what's happening with accelerating charges. Now, how do you make gravitational waves? I'm going to tell you something, and if you promise me, you're not going to tell it to anyone outside. It's a secret. I'm going to give you a physics secret nobody knows about. How can you make a gravitational wave? Move. Every time you move, you create a gravitational wave. It's a bit small and you can't really detect it, but it doesn't matter. Okay? When you dance with your partner, you create gravitational waves. Anytime that you move around, you create gravitational waves. Their amplitude is so small you cannot detect them. But it's happening. Non-primordial. Primordial is what happened in the very beginning of the universe, when the universe was, in some way, came to be. Non-primordial is kind of local. Local, I mean not in Lorentz, but local meaning not in the early universe, but since then. So things that happen around in the universe, but not in the very early universe. The first indirect evidence for gravitational waves was done by looking at pulsars, which are two neutron stars going around each other. As they move closer, they radiate gravitational waves. That's why their orbit decays, and they come closer and closer to each other until they collide. Every two bodies that go around each other radiate gravitational waves. And when they radiate gravitational waves, you radiate energy away, so the orbit between them decays. In other words, they get closer and closer, and the time of orbit is shorter and shorter. That happens when the moon goes around us, when we go around the sun. Okay, so our orbit around the sun also decays because of that. It's going to take about 10 to the 150 years for the orbit to collapse completely because of gravitational waves. So we're fine. But in general, every two bodies radiate gravitational waves. But in order to detect them, you need some things, two bodies that are first very massive, two close enough. So you can actually measure these things. The first people that actually observed that are called Halson-Taylor. So they call the pulsar Halson-Taylor pulsar. And these are these kind of numbers. Physicists have absolutely no imagination. And they come out with ways of naming things that, well, I do not understand it usually. It has something to do with, well, PSR is pulsating something radio. And these numbers are where it is in the sky. In 1974, Halson-Taylor discovered a signal of pulsar around with the Arecibo radio telescope. Here it is in Puerto Rico. And what they did is they saw this pulsar, and it's rotating at sends a beam of very high energy and radio waves. Pulsar is a very small kind of thing, about 15 kilometers, 10 miles across, and it has the mass larger than the sun. Okay, the sun, remember, has mass about 1 million times the Earth's mass, and you can put it all in Lorentz. So it's a rotating thing, and it hits the Earth, the radiation hits the Earth, and this particular one has a period of 59 milliseconds. So it turns around a little bit less than about 20 times a second. You have pulsars that are going around from between about 7 times a second to tens of thousands times a second. Very, very fast. Okay, what they discovered in this pulsar is that its period varies over a period of 7 hours and 45 minutes. That means that the pulsar is actually going around. It's not just by itself spinning, but it is going around another companion that we cannot see. So if you have these two massive stars going around each other, general relativity tells you that their orbit must decay. So Halson Taylor actually measured that and showed that the decrease is exactly as predicted by general relativity. So the dots are their data, and the line is general relativity. That's what general relativity says this is going to happen. They got the Nobel Prize for this discovery in 1993. And since then, many, many other pulsars, binary pulsars, were discovered, and all of them have a decay of all orbit, which is exactly what general relativity suggests. Now, the reason, as I said before, the reason why the orbits decay, as you can see here, is because they radiate gravitational waves. We didn't see the gravitational waves, but we saw the effect of the radiation on the orbit. Okay, so as I said, accelerating masses change the distortion of space-time and radiate gravitational waves. Here are a simulation of two black holes. Because black holes are even more massive than pulsars, when they merge, they create a very strong high amplitude gravitational waves. Okay, so this is basically what LIGO was trying to look for. Because when you have two pulsars like the ones that Halson Taylor found and many other ones, they're still far away and they do not, their orbit is decaying, but they didn't merge yet. The highest signal is when they actually merge. Okay, so LIGO are looking for these kinds of events, the merging. So here is a simulation. So basically what you have here are the two black holes. This is the curvature of space-time. The color here is the depth is the curvature. The color is how fast time flows, and the arrows are how fast matter flows. Here you have this wave that tells you what is the amplitude of the gravitational waves that they're emitting. And as you can see, when they come very, very close, you have higher amplitude. They slow it down just to show it better. The black holes are getting closer and closer to each other. You have very high amplitude. The highest amplitude is when they merge. And then you have ringing. And that's it, and no more gravitational waves. And that's a signal that they were looking for.
Why is this signal zero? It's a rotating, right? Angular momentum conservation.
Right, but it doesn't. Yeah, well,
but it's a rotating.
it's but the the amplitude of the gravitational waves after they merge are very, very small.
Okay, so it is there, but it's small.
It's, yeah, but almost non-existent. And it's because of the rotation. Okay, so here is simulation of two black holes, edge on, so you look down. Now, black holes, from the name you can understand, they don't emit any light. Okay, so you can't see them. The only reason you can see them is by the effect of light from stars and galaxies from the backside going at you and being distorted by the black holes. But they themselves do not emit any light. Here is another simulation that I kind of liked that has edge on. So you have this way, smaller black hole and a larger black hole, and you can see they merge, and then they have this ringing thing, and then that's it. They have the black hole itself. This is a three-dimensional simulation. I just like the colors, so. That tells you, again, two black holes, and that's the full effect of gravitational waves coming out. And they also show the magnetic field, the gravitational field itself. Now, it's very confusing because there are too many things going on, and you can't really see them because obviously we take three-dimensional stuff in time and we project it on a screen, and it doesn't show very well. So what we do usually when we want to show things is that we do two-dimensional plus time. So this is this thing, again, you have the two black holes, the green, the light green, and the dark green are telling you about when space is stretched and when space is contracted. Okay, so if you have something, it expands and contracts, expands and contracts. Then the gravitational waves move through. Everything is transparent to it, so it just moves through the universe, causing some vibrations, and then reaching the Earth and changing the time, the distances in the Earth. Now, as it says here, scale of effect is vastly exaggerated. Now, by vastly exaggerated, I would say about 40 orders of magnitude. Okay? So when they say vast, they mean vast. Okay, so how do you detect this thing? You have an interferometer, and I'll talk about how this thing happens, but first a little bit of geography. You have two detectors, a little bit better geography, Google Maps. There is one in Hanford, Washington, and here is one in Livingston, Louisiana. And here is the detector itself. Okay, so interesting things. First of all, you have two mirrors that are 4 kilometers apart. Okay, interesting thing about it, when you make what you need is exactly straight line between the two mirrors. Okay, now the curvature of the Earth is such that over 4 kilometers there is a drop of about 1 meter. Okay, so to actually create this tube, it's a vacuum tube, and the two mirrors, you have to make it very, very accurate to have these two mirrors exactly parallel to each other and exactly in a straight line. Okay, now this is one of the things that they did. Basically, the Earth is a living kind of thing. There's seismic noise and winds and stuff. These guys can figure out that people are cutting trees next to the observatory. Next to, I mean, 30 miles away. Okay, so what they do is that they take these mirrors and they hang them. Now, I brought a demo that I asked our demo person to make for me. Now, I just want to say one thing before I show you the demo. That's a pendulum type thing. Okay, I'm a theorist. I don't know how to make anything work. Okay, so if this does not work, it's not because they don't know what they're doing, it's because I don't know what I'm doing. Okay, so the idea here with a pendulum like that is that when I move it slowly, everything moves with me. Do you see, everybody sees what I'm doing? Right, everything moves with me. But if I move this, well, this is not supposed to move, okay? Like that. If I move this quickly, this stays the same. So basically, if the Earth around the observatories is shaking for some reason, it doesn't affect the mirrors. The mirrors stay straight. Okay? That's the idea of hanging it on very, very thin lines that basically do not move the momentum down. So the fact that the ceiling from which they're hanging is moving does not affect the mirrors themselves. Okay, so here is an interferometer. Creates a laser beam, splits. These mirrors, they move because of gravitational waves. They change the distances between this and that. So basically here it is. You have a wave. It splits. One goes to this mirror. The other one goes to the other mirror. They come back. They recombine in this mirror and go to the detector. Okay? To begin with, they're exactly out of phase, meaning where there is a trough, there is a hill there. So there's no light hitting the detector if the two mirrors are exactly the same distance away from this mirror. But if they move, then there is light, and you can measure that. And what you measure is actually the light on this detector. Okay, when the mirrors are exactly the same distance, you see no signal. I'll show you another kind of simulation like that. And they kind of show this out of phase type of light. So splitting the beam, one goes this way, one goes this way, exactly the same wavelength for each one of them in a laser. They combine and create this. So right now, there's no light because this one cancels this one cancels this one. Okay, so right now the detector sees nothing, but if this one gets closer and this one further, or vice versa, you see a signal, and that's what they were measuring. Light, no light. Interferometers are totally cool. I never operated one, but I know what they're doing. Okay, this is an atom-ish. Okay, and if you go close, about 5 orders of magnitude smaller than the atom is the proton. And we can see something about 10,000th of the proton diameter with this interferometer. Okay, so what's happening again, as I mentioned before, but I'll show you a diagram. You have these inspiraling. Okay, this is the kind of signal that you have when they're reasonably far away but starting to get closer. The closer they are, the higher. There are two things happening. Both the amplitude gets faster, and because the orbit decays, meaning the orbit is shorter and shorter, the wavelength is shorter and shorter. And this just tells you the speed, the relative speed of the black holes a third to almost half of the speed of light. Just think about it. These black holes are massive. They are 30 times the mass of the sun. They're moving at half the speed of light. And the separation is the black line with these numbers, separation in terms of their radii. Okay, so you have the in-spiral, you have the merger, and you have the final product. What they found, they matched it to predictions of general relativity, and they're given the fact that there are two black holes, 36 and 29 sun masses each. The final black hole is 62. In other words, there are three masses of the sun that are radiated in gravitational waves within less than a second. During this less than a second, this collision released 50 times more energy than all the stars in the universe combined. It was pretty incredible. And this is the kind of signals. The Hanford is the whatever orange, and the blue is the Livingston. And they are, because they are oriented differently, the two things, and it takes time for the gravitational waves that move at the speed of light to move from, they first hit Louisiana and then they hit Washington about 10 nanoseconds later, and because they're oriented differently, you had to invert the signal. So when you invert the signal, you get these things. I'll show that to you a little bit and again. But basically, they fit really well. Here they are. So these are the Hanford and the Livingston, and the two of them after you shift and invert. Another fun fact, the largest noise for the detectors are ocean waves. Okay, these guys, especially the Washington one, is almost 100 miles away from the ocean. Largest noise in the detector are the ocean waves. Gravity waves interfere with the detection of gravitational waves. Brothers don't like each other kind of thing. Okay, this I'm going to put some sound in. Let's see if that works. So actually the frequency of the collision is actually frequency that we can hear. So what they did is that they recorded this and turned it into sound, and then made the sound frequency a little bit higher so we can hear it better. We can hear both of them, but one of them is really kind of low. So here it is. The duh. Whip, whip. That's the one. That's the collision. Whip, whip. That's the collision. The duh, duh. The rest is noise in the thing, and then the collision comes and it has this thing. Did you hear it? Do you want to hear it again?
The chirp isn't very high amplitude above the noise, is it?
No, it's not. You can see it. You can see it here in the. That's the noise, and that's the chirp. So let's try to do it again. I think that the event is much more fascinating than the noise, but once they have lots of them, maybe they can make some music. But okay, so let me just kind of take a step backwards and kind of talk a little bit about this, and I'll come back to the gravitational waves. In general, when we look at the universe, and if you talk to any astronomer, they will tell you, when you look at the universe in different wavelengths, you see very different things. Why? Because in order to emit light, you have to have some kind of events, and different wavelength of lights come out from different energies of events. Okay? Very, very high energy stuff emit gamma rays and X-rays. Very low energy stuff emits radio waves and microwaves and stuff like that. So here, for instance, is this another one of the names, astronomy names, NGC 1512. It's a galaxy, as you can see, and these are the images of the galaxy in different wavelengths, and this is a combination of all of them together. Okay, so what you see here is, again, you see kind of stars here or whatever, light here that does not really exist here. If you look at the whole kind of sky, well, this is kind of directed to the center of the galaxy. This is the center of the galaxy in all of them. And again, from radio, atomic hydrogen, radio continuum, molecular hydrogen, infrared, mid-infrared, near-infrared, optical X-rays, and gamma rays, and you see very different kind of things. In some places you see these things, and here they don't exist at all. Very, very bright sources that don't exist here or here, and so on. Here's another kind of a movie that suggests that, from visible to larger, longer and longer wavelengths. And if you change also the contrast, you see very, very different things. Okay, in fact, we started being able to see the universe in anything but radio and optical wavelengths only in the last 50 years or so. Because we have this thing, a very pesky kind of thing that is on Earth. It's called atmosphere. And it blocks everything. And we don't like it because we can't see anything through it. But we're stuck with it, so what do? We send satellites or balloons or whatever up above the atmosphere, and then we can see different wavelengths. So here's another, that's only in the microwave, but different frequencies. And mainly, look, this is the galaxy, and the emissions from the galactic disk, which we're sitting in it, is very different across different frequencies. And that's only in the microwave. Just imagine when you move to gamma rays. Here's another way of showing the same kind of thing. Radio waves, microwave, infrared, optical, X-rays, gamma rays, and gamma rays with the sources in them. You see very different phenomena when you look at the universe. And every time that we made some kind of telescope that can look at different wavelengths, we found things that we didn't imagine existed. The universe has much more imagination than we do. Okay, so let's go to primordial, meaning things that happen very, very early universe. Most of the things we don't really understand. Phase transitions we knew happened. Okay, phase transitions meaning same kind of thing as what happens when you have ice and you heat it up and it turns to water. Behaves very differently, and yet it's exactly the same substance. Same kind of thing happened in the early universe when forces and things like that kind of decoupled from each other, and we went through a phase transition, and the rules, the laws of nature in some way changed. Not so much the laws of nature, but how things behave under the laws of nature. Cosmic inflation, we don't know if it happened, but we think it probably did. Topological defect, we don't really understand. We never saw one. Extra dimensions, we have no idea if it's there. String theories is another pipe dream that nobody knows if it exists. But we're physicists, you know. We come up with all kinds of ideas. And some of them actually turns out to work. Like, for instance, gravitational waves seems to be true. And that was predicted 100 years ago. Started designing the whole apparatus about 50 years ago. And all of a sudden, September 14th, we found it. February, they they actually discussed it in public. Okay, so first of all, cosmic inflation, which again, we don't know if it happened, but it simplifies everything, and physicists love simplification. What is it? The idea here is that the very, very early universe probably underwent a very sudden and exponential expansion about this kind of time. Now, because you're nerds, I assume that you know what I'm talking about, but it's very, very early on, very close to the Big Bang itself. And the universe expanded from a size much, much smaller than a proton, about 12 orders of magnitude smaller than a proton, to the size of a grapefruit. Okay, now you think this is, what's the big deal? From here to here, it's not a big deal, but just think about that light travels 10 to the minus 25 meters and about 10 to the minus 33 seconds. So 10 centimeters or 0.1 meter takes a great deal more, about 24 orders of magnitude more, for light to travel this thing. So it was a much, much, much speedier kind of event than what light can travel. What caused this expansion? Again, first of all, we don't know that this expansion happened. Okay, remember that. Second, we don't really know, but a good explanation is that at this time, all the four forces used to be one force, and at that time, they decoupled. It doesn't work that well because the energy scales are a little bit screwy, but it gives you an idea. We went through a phase transition, okay? And during phase transitions, you release a lot of heat, a lot of energy. Or you depends on which direction the phase transition goes. But this kind of phase transition releases a lot of energy. So because you had this incredible expansion, incredible acceleration, you generated a lot of gravitational waves with some characteristic amplitude. It depends on how fast this expansion happened and when it happened exactly. What was the strength of these gravitational waves from defects depend on their mass scale. Again, we don't know if their defects are there. So, but if there are defects, they will generate gravitational waves. And so if we detect gravitational waves from defects, we will know a lot about defects. The internal energy of some modes from extra dimensions can be released. And again, if we find this thing, we will learn about string theories, about extra dimensions, about things like that. Now we're very far away from being able to do that, but we found something new. Let's go with it. Okay, so what's so great about gravitational waves? They're radiation that is unlike any other type of radiation. All the radiation that we can detect comes from electromagnetic waves. Okay, light basically. Light in different wavelengths. In general, radiation carries energy, and energy is information about the source. So if you find some light, radiation coming from a source, you know what the source is doing. That's the way we learn about things that are far away that we cannot touch. So gravitational waves carry information about motion of objects. They're not absorbed or reflected by the matter, the rest of the universe, so you see all the way to the event that caused them. Now, the universe is transparent to gravity virtually right after the Big Bang. Unlike light, the universe was opaque to light or to any kind of electromagnetic radiation for about 300,000 years after the Big Bang. So we cannot see with radiation, with electromagnetic radiation, anything further than about 300,000 years after the Big Bang. With gravitational waves, we can see all the way to the Big Bang because the universe is transparent to gravitational waves. So we'll be able to see through objects between the Earth and whatever the source is. Every time we open new eyes on the universe, we learned a lot of new things. So just by going with this idea, gravitational waves opened a new window to the universe, will probably teach us a great deal. We knew that black holes exist. We knew that probably there are some binary black holes because there's such a big universe, but it shows us that we can do something. Now here is, it's called Planck. It went into a place outside of it's a satellite, and it just scanned the sky in electromagnetic microwave light. And it looked at the first light, the first electromagnetic radiation that came out in the universe. But it also looked at closer by things, and as you can see, you see very different things when you look at different scales. And the Planck satellite, although it mainly looked for the microwave light that came from 300,000 years after the Big Bang, they also looked at other things like galaxies and clusters of galaxies and molecular clouds and various kind of things that emit electromagnetic radiation. But they mainly looked, they only looked with electromagnetic radiation. They cannot see anything else. But they found an incredible amount, and we learned incredibly a lot about the universe, its evolution, and what happened since this time. We, not only through Planck, but we discovered that the way galaxies organize themselves on large scale is what we call the cosmic web, and it's connected to what happened in the last scattering surface, very early universe, that evolved because of gravity to become this distribution that we see today. Okay, so basically we saw kind of baby universe in some way, well, maybe not baby. I think I call it the toddler universe, because 300,000 years is not the baby. And we learn a lot of stuff about this. Its age, its composition, its evolution, all kinds of stuff. We also found things that we don't understand. Keeps us employed for another whatever. But basically, this is the toddler picture of the universe. Now with the gravitational waves, if all goes well, in about, 200 years, we'll be able to do exactly the same thing, but actually see the baby picture of the universe. And we all know when we look at ourselves, we were much cuter when we were babies than we are today. And chances are that even today we're cuter than what would be tomorrow. So baby is the way to go. Okay, so this is basically what LIGO found, and this is the connection to the rest of our exploration. So what's going to happen in the future? For LIGO, they're building some more detectors. There are the twin detectors in Hanford and in Livingston. There is another one that is just becoming operational in Germany. There is one in Italy and one in Japan that are being built, that are actually undergoing upgrades. They're also already built. And there is one that is being planned in India. And the more you have, the more accurate you can have these correlations between the signals. You can do various things like point and know where it actually is, because it's very difficult to find where these two things are in the sky because you have only 2 points. So this is the map. So basically, these are operational, these are upgrading, and this one is planning. So that will happen within the next 10 years or so. We will have all of them operational. Beyond LIGO, we have as I showed you before, the cosmic microwave background radiation satellites actually looked at all the frequencies in the microwave from this radiation from the toddler universe. The same kind of idea you can think of to do with gravitational waves. So they came up with something called LISA, Laser Interferometer Space Antenna. It started as a joint project between NASA and ESA, the European Space Agency. NASA dropped out because of monetary constraints. So under ESA, the LISA Pathfinder, which is kind of a satellite that was launched just last month or a couple of months ago. It's a forerunner mission that will test the technology. And then from that, they will take the evolved LISA, ELISA. Again, we're physicists, right? We have great naming schemes. And it will be launched in 2034, if all goes well.
None of us will be around.
Yeah, well, we'll still be around. I mean, what, 34? Not that far away in the future. So basically where they're going to send it is to what we call in our great naming scheme, it's called L1, which is a place which is kind of an equilibrium point between us and the sun, Lagrangian 1 point. And that's where both the Planck satellite that I showed you the pictures from and the WMAP satellite that went a few years before that are hanging out. It's kind of a very popular resort. And so they're going to send this LISA Pathfinder to hang out there for a while. And so between us and the sun, and it's going to communicate with the Earth and kind of do all kinds of experiments and stuff like that, figuring out what they do. But it's mainly, this one is not going to measure any gravitational waves. They're going to try to see if we can put an interferometer up in space over there. So this is about the Pathfinder. It's kind of getting late, so this is LISA. Okay. The idea is that you put 3 mirrors about the original LISA with NASA and ESA was supposed to be about 5 million kilometers between each one of them. And they're sending lasers, okay? Because NASA pulled out, they're scaled it down a little bit, and it's going to be about 1 million kilometers each one of those things. So basically, you're going to have these 3 detectors. They're going to send laser beams between them, and they're going to be in an orbit around the sun with very precise distances between these 3 mirrors. And they're going to look for it. As you can imagine, the longer the baseline is, the more accurate you can measure distances or difference in distances. So this is the idea here for the future prospects. And these are the kind of how accurate they can measure it. Don't worry about it. I mean, this is basically how accurate they can measure it. And LISA was here, and as you can see, ELISA is not as accurate. Now, because of the distant differences and stuff like that, they're looking also at different frequencies. Different frequencies will show you different populations of things. Okay, so we covered everything. And I think that I'm pretty much on time, 55 minutes. Thank you.